So today, class, we're going to begin talking about how we determine whether or not a deductive categorical syllogism is valid or invalid. Now, before we get started, I want to remind you of our definitions of what validity and invalidity are. And as you should know at this point, an argument, a deductive argument, is valid just in case if the premises are true, then the conclusion must be true. It is that hypothetical relationship that exists between the premises and the conclusion. Whereas it's invalid just in case it's possible for the premises to be true and the conclusion to be false. Now you might wonder, well, why in the world are we studying deductive validity in detail anymore? I mean, after all, we learned how to prove whether or not an argument is valid or invalid. We simply think of a counterexample. That is, we imagine a scenario in which the premises are true and the conclusion is false, and then we proceed from there. And if we can devise a way in which the premises are true and the conclusion is possibly false, we prove that the argument is invalid. Now this method serves us pretty well probably for a majority of cases we encounter. But there are many times where our intuitions on the matter just fail us, where it's just we can't really conceive of a way in which the premises can be true or can be false, not because there isn't one, but just there are limitations to our imagination and to our, as I said, intuitions. So I want to give you guys a couple of examples, and I want you just to look at these three arguments. I want you to pause the video lecture and go through and see if you can determine whether or not these arguments are valid or invalid. Just kind of relying on your own ability to devise counterexamples or your own sense of logical relationships. Just pause it, work through these very briefly, and see if you can't devise or determine, I should say, whether or not these arguments are valid or invalid. So I hope you did take the time to go through these and try to figure out for yourself whether or not these arguments are valid or invalid. Let's look at them very briefly and see if your answers are the correct ones. So all mammals, we're looking at number one. All mammals are warm-blooded. No reptile is a mammal, therefore no reptile is warm-blooded. And this argument you might think is valid, but it's actually an invalid argument. And it's hard to explain why it is at this point. Once we study what I'm going to discuss today, which is Venn diagramming arguments, it'll make a lot more sense. But this argument is invalid. It doesn't work. I think a lot of times I encounter people who find that it's valid, and the reason they do is because if you look at it, all the premises are true. All mammals are warm-blooded. Yeah, no reptile is a mammal. That's true. No reptile is warm-blooded. I believe that's true also. So everything here looks true, but the problem here and the reason it's not valid is because even though 1 and 2 are true, they don't guarantee the truth of the conclusion. So I'll explain why that is later on. Argument number 2, no mammals are warm-blooded. Some mammals are snakes, therefore some snakes are not warm-blooded. And this argument you might think is actually invalid, but the truth is it's perfectly valid. You might think it's invalid because, well, the first premise is false and the second premise is false, but that's not what determines validity. Validity, that would actually speak to its soundness. If you recall from a long time ago, we distinguished soundness from validity. What makes an argument valid is just, again, that hypothetical, if the premises are true. And here what you have to do is you'd have to assume these premises are true, and assuming 1 and 2 are true, must the conclusion be true? And the answer to that is yes. All right, number 3, some plants are not edible things. All poison ivy plants are plants. Therefore, some poison ivy plants are not edible. I hope you don't eat any poison ivy. It'd be really bad for you. But if you do it on the basis of this argument, you've done it for invalid reasons. This argument is also not a valid one. Now, everything about it seems right. Some plants aren't edible. That's true. All poison ivy plants are plants. Yes, that's true. And it's also true that some poison ivy, in fact, all of it, I would assume, is not edible. But even though everything here is true, the 1 and 2 do not actually guarantee 3. And why this is, we'll come back to later on. But the important point I wanted to demonstrate here today, maybe some of you got all these right. If you did, I don't know if I'm going to sell you on what I'm trying to sell you on now. But I assume that most people got at least one of these incorrect. And what I'm trying to sell you on is that we need a better method for detecting validity and determining validity for these arguments because, like I've said, our just gut intuitions don't always serve us particularly well. They're not always accurate. So what we're going to do is we're going to actually learn two methods for determining validity. One that actually proves validity, and then later on we're going to come back and we're going to look at some rules that actually do a better job explaining exactly why an argument is invalid. But what I want to work on now is the method of proving whether or not a categorical syllogism is valid or invalid. And to do that, what we're going to do is we're going to use our Venn diagrams. Now, hopefully at this point, you are somewhat comfortable with Venn diagrams. We've been using them so far in order to show logical consistency. And as you've seen in the previous cases, what we've done is we've diagrammed a proposition, right, where we just say like all S are P, and then we diagram that single proposition. Well, at this point, we're actually going to be diagramming not just one proposition at a time, but we're going to actually diagram two propositions at a time. Because what we're going to be diagramming, we'll just go back a slide, is we're going to have actually two separate diagrams. We're going to diagram the combined premises, excuse me. We're going to have one diagram for the combined premises, and then we're going to draw a separate diagram for the conclusion. Now, and so far as we're diagramming the conclusion, it's going to be just the exact same as before. We're going to have our S and our P. If you recall, when we put it into standard form, the subject here is S and the predicate here is P. But how are we going to diagram the combined premises? Because in the past, what we've done is when we diagrammed a single proposition, we've had two circles, right? This circle right here, the S represents the class of things in the subject term. The P represents the class of things in the predicate term. But if you look at the combined premises, going back a slide, we don't have just two terms. We have three. We have our minor term, reptile. We have our major term right here, the predicate. And then we have our middle term that's occurring right here. So how are we going to diagram these three terms? Like I said, the Venn diagrams have worked really well when we've had two terms. What do we do about a third? Well, some of you might have guessed it from all my build-up, but what we do is we have to introduce a third dimension. I'm just calling it that, but we have to introduce a third circle. And this represents the middle term, which is why I have the M here. Now, this is really jumbled and it looks kind of crazy what's going on, but keep in mind that the M is just representing the region of overlap between the S term and the P term, between the minor term and the major term. Now, when we go back and we think of our normal Venn diagram, how many regions do we have? Well, hopefully you recall we have 1, 2, and 3. Well, look at this. How many regions do we have here? Well, we got a lot more, and I'll just cut to the chase. We actually have 7 different regions that are represented. Now, this looks kind of complicated and overwhelming, but the truth is it's just more of the same thing you've been doing. And the methods we use to diagram the combined premises is really no different than anything we've been doing thus far. In fact, I think you'll find that once you get in the groove, it's kind of straightforward and pretty easy. Now, what we do is we combine the two premises and we construct a Venn diagram for those. And then we also construct a Venn diagram for just the conclusion. And so the steps here, I just want to show you the steps, spell it out for you. For Venn diagramming a syllogism is, first we diagram the combined premises. And yeah, I have in parentheses here, right, you'll see you do the universal premise and then the particular ones. I'll come back to why that is. I'll talk about that in a minute. But we diagram the combined premises, and then we diagram the conclusion. And then once we've done that, we determine whether the information combined in the premises proves the conclusion true. Now, as I say here, the diagram of the premises may contain more information, but it can't contain less. And when it comes to doing step 3 here, it's different for what we do when we're talking about a universal conclusion versus a particular conclusion. So if you look back at the arguments I presented, sorry, I got to go back a few slides. If you look right here, this conclusion is a universal, right? It has the universal quantifier no. If it had a universal, or if it had a quantifier all, it would also be a universal conclusion. But this conclusion is particular. Some are not, and then this is some are not. If it just said some are, that would also be particular conclusion. And like I said, we do different things when we have a universal conclusion versus a particular conclusion. When we have I say categorical here, I should have said categorical, universal, but we have a universal conclusion. Basically, what we do is when we diagram the conclusion, the regions that we shade in the conclusion also have to be shaded in the combined premises. Now the combined premises may shade more, but they can't shade less. That's why I said up here that the premises may contain more information but not less. When we diagram the universal conclusion, the regions, let's say if we diagram the universal conclusion and let's say we shade in regions 2 and 3, well then the combined premises also have to shade in regions 2 and 3. They could shade in 2, 3, 4, and 5, but they have to shade in at least 2 and 3. And this is all really abstract right now. It's going to actually make a whole lot of sense once I give you some examples. But when it comes to a particular conclusion, it is going to be a little bit different. And what we have to do is, in this case, basically the combined premises have to definitively put an X in the region or one of the regions that the conclusion says the X belongs in. So all of this is really confusing because you're not seeing this kind of like live action. So I'm going to give you guys some examples of this, and it will make a whole lot more sense once we start doing some of those examples. So just give me a moment here so that I can pull this up. Our trusty marginally functional app here. All right, so let's suppose we wanted to determine whether or not a categorical syllogism is valid. Well, let's give a categorical syllogism. I'm going to begin by just coming up with one. We'll say no M is P, premise 1. 2, we're going to say all S are M. And then 3, we're going to say no S is P. All right, and what we want to do is we want to figure out whether or not this is valid. And the way we're going to do that is, as I was saying a second ago, we're going to draw a Venn diagram of the premises by themselves, and then we're going to draw a second Venn diagram of the conclusion. So let's begin by drawing a Venn diagram of the two premises. Well, we're going to begin by, let me give myself a little space here. There we go. We're going to begin by coming up with our region. So we have a circle for S, one for P, and now what we need is we need one for M. Okay? And I'm going to just write out the letters here, S, P, M, and then we need to number the regions. And I mean, we don't need to, but it does make things a little easier. Region 1, which you can see is basically all of this area right here. That's region 1. All right, I'm not going to do it for all of them. Then we have 2, 3, 4, 5, 6, and 7. Now, I'm going to make the, we've used the numbers a lot in the past, and I do find that the numbers are very, very useful. But I want you to think about this. What region is M equal to? What regions are contained in that? Well, it's 1, 2, 3, 4. That's the regions of M. And then what region or S? Well, S is equal to 2, 3, 5, and 6. And how about P? Well, P is equal to 3, 4, 6, and 7. So like I said, I mean, what we're going to be doing is basically the same thing we've done before. It's not going to be any different. We're just going to be doing more of it. So the way we diagram the combined premises is we just start and we diagram, let's say we diagram number 1. No M is P. And I'm writing this over here so you can see it. Now, as I say up here, M is 1, 2, 3, and 4. And P is 3, 4, 6, and 7. And so the way we diagram this is we just do what we've done before, which is we circle the regions of overlap, which is 3 and 4. Circle those. We get rid of these because we don't care about those. And then what we're saying is nothing is in 3 and 4. So we shade in 3, we shade in 4. And so that's pretty straightforward and easy, just everything like we've done before. Then we come down here. I'm going to erase this so I have some room to work with. And then what we're going to do is we're going to diagram premise number 2. And what does 2 say? All S are M. So we do the same thing. We say S is 2, 3, 5, and 6. M is 1, 2, 3, and 4. We circle the regions of overlap, which is 2 and 3. We scribble out those that we don't need. And we're saying all S are in M. So all the S are in 2 and they're in 3. So where are the S not located? If they're all in 2 and 3, where are they not? Well, they're not in 5 and 6. Now, we also know that, as it turns out, there are no S in 3 because, and we know that from premise 1. Premise 1 ruled out there being any S in 3. So the only S actually that exist are in region 2, as it turns out. And the reason they only exist in 2, that's due to combining 1 with 2. Since 1 basically says no M or P, what that does is when we shade out 3, that means is void. Nothing is in there. And so it rules out there being any S in M because it rules out anything existing at all in M. Okay, so now what we do is we're going to diagram the conclusion. And to diagram the conclusion, we do that just as we've kind of done the other 2 premises. If I can get my trusty circle to come up here. There we go. We come over here. And it's going to be, everything is going to be the exact same. We're going to label the regions S, P, and M as before. And we have 1, 2, 3, 4, 5, 6, and 7. Now, I think I have enough room to work with down here at the bottom, but we're going to be diagramming no S is P. No S is P. And S is equal to 2, 3. That's not a well-written 3 at all. 2, 3, 5, and 6. And P is 3, 4, 6, and 7. And just as before, we circled the regions of overlap. So what are the regions? It would be 3, right? And then 6, just like this. And then we scribble this out because we don't need that. And what this is saying is no to 3 and 6. So what we do is we shade in 6 and we shade in 3 because we're saying nothing is in there. And now the question is, are the regions that are shaded in right here, are they also shaded in over here? And the answer is yes, they are. 3 is shaded in here, 3 is shaded in the combined premises. 3 is shaded in, 6 is shaded in the conclusion. 6 is also shaded in right there. And so this argument is yes. I'm running out of room. It is valid. This argument is valid. And that's how we prove validity. Is basically when we're dealing with the universal conclusion, if the regions shaded in the conclusion diagram are also shaded in the combined premise diagram, the argument is indeed valid. Well, let's do another one so that we can see how this works. In fact, I'll do a couple more because the more practice you get, the better it's going to be. So let's see, and I'm going to have to delete this one over here just because I'm going to need room to work with. So let's write an argument up here. All P are M. We're going to say all P are M, and all S are M. All S are M, and then 3. All S are P. All S are P. Does anybody know the mood and figure of this? AAA, figure 2. Just in case you need to remember that stuff, just in case you've forgotten. And we're going to do just as before. We're going to number 2, 3, 4, 5, 6, 7. Okay. Now, we're going to begin by diagramming number 1, which is all P are M. And P is equal to regions 3, 4, 6, and 7. And M, 1, 2, 3, 4. And what regions overlap? 3 and 3, 4 and 4. And we scribble this out. And we're saying all P are M. So all the P that exist are in 3 and 4. Well, if all the P that exist are in 3 and 4, where are they not? They're not in 6, and they're not in 7. So that's how we show that. We shade in 6 and we shade in 7. Now, let's do the second premise, the minor premise. All S are M. S is equal to regions 2, 3, 5, and 6. M, 1, 2, 3, and 4. And what do we do? Well, circle the regions of overlap, which are 2, 3, 2, and 3. And we cross out these because we don't need them. We're saying all S, that looks like a J, all S are M. So all the S are in 2 and 3. That means no S in 5. And lo and behold, we don't even have the shade in 6 because it's already been shaded in. So this would be the diagram of the combined premises. Now, we have to move on and diagram the conclusion. And so in order to do that, we have to draw another Venn diagram over here. And just as before, S, M, P. Now I should say there's nothing magical about putting S here, P here, and M here. The truth is we could, if we wanted, put P at the top, M over here, and S over here. The only thing is if we did that for this diagram, we'd have to do it for this one as well. They have to match, because if they don't match, it's going to throw everything off. So if I if I had M for the bottom left circle, I'd have to have it for the bottom left circle for the combined premises as well. There's really no logical reason why S has to be here, P here, and M here. In fact, sometimes students they'll just kind of draw their diagrams a little differently than mine. They'll put, good gravy, I'm having trouble here. They'll put this circle down here like that. That doesn't change anything logically if you did that. It doesn't change anything, not from a logical point of view. So the only rule is you have to be consistent from your combined premises to your conclusion. If you're not, it'll just throw everything out of whack. So now we're going to diagram, and we can number them if we want. 4, 5, 6, 7. We're going to diagram the conclusion. All S are P, and S is 2, 3, 5, and 6, and P is 3, 4, 6, and 7. And what we do is we circle the regions of overlap, which are what? 3, 3, 6, 6. We scribble these right here out. They're not needed. So we're saying over here that all the S are in 3 and 6. So all the S are in 3 and 6, which means they're not where? They're not in 2 and they're not in 5. So here's the question. Is this argument valid? And the answer to that is no. It is invalid. Why is it invalid? Because in the conclusion we shaded in region 2 and 5. Now over here we shaded in 5, but notice we didn't shade in 2. And since 2 is not shaded in over here, the argument is not valid. So that's basically what you're looking for when you're dealing with a universal conclusion. You're looking for a case where you have the regions shaded in the conclusion. If they're shaded in the conclusion, if like 2 and 3 or 2 and 5 are shaded here, they have to be shaded over here as well. If they're not, then you have a problem. Now the conclusion, the combined premises can always shade more. For instance, suppose I'd shade it right here. Let's say I'd shaded this whole thing. Would the argument be valid at this point? And the answer is, yeah, it would. I mean, you could shade in everything over here. I don't know how that would ever work, but let's suppose you had. But as long as the region shaded in the conclusion, if the conclusion shades in, let's say the conclusion shaded in 1, 7, and 5, well then the combined premises, they had better shade those regions in. If they don't, then the argument is not going to be valid. So that's what I'm trying to communicate to you right now. When we're dealing with a universal conclusion, now this only applies to a universal conclusion, and we'll talk about what we do when we deal with a particular conclusion in just a minute. I want to give you a quick one for you to practice, and you're going to have to pause the video lecture in order to do this. But I want you to do the following all on your own. Just pause it and do this one. So, no M is P. Let's say all M are S. That says R in case you're wondering. And all S are P. Oh goodness, I've left off. Sorry, why'd you guys let me do that? Why'd you let me leave off my number here? Number 2. All M R S, and then 3, all S or P. All S R P. And what I want you to do is just pause the video lecture here and see if you can't determine whether or not this is valid or invalid. So go ahead and pause it and work on that. All right, well, I hope that you did pause it and you did try your best on it to determine whether or not it's valid or invalid. I'm going to show you the answer to it just now. So we're going to construct a Venn diagram of the combined premises just as before. And we're going to begin by numbering our regions just because I find it helpful. Some of you may be able to just do it without numbering them, and that's fine. But we're going to begin by doing premise 1. No M is P. And M is equal to region 1, 2, 3, and 4, whereas P is 3, 4, 6, and 7. And what we do is we circle the regions of overlap, which are 3 and 4, 3 and 4, scribble those out, we don't need them. And we're saying no to 3 and 4, so we just shade in 3 and 4. All right, so that's how we do that part. And then we're going to do premise 2. All M are S, and M 1, 2, 3, 4. Just out of curiosity, what's the mood and figure of this argument? It would be EAA3, just in case you're wondering. S is going to be 2, 3, 5, and 6. And so we locate the regions of overlap, which are 2 and 3, 2 and 3, and then we scribble that out. And we're saying all M are in 2 and 3, which means if all of them are in 2 and 3, where are they not? They're not in 1, and they're not in 4. But we don't need to shade in 4 because we've already shaded that in, so that's taken care of. All right, well, now that we've done that, we have to do a Venn diagram of the conclusion. And so let's do that. We draw our circles just as before. And let's see, we're going to do S, P, and M. 1, 2, 3, 4, 5, 6, 7. And we're going to diagram all S, R, P. And let's see, S is 2, 3, 5, and 6. P is 3, 4, 6, and 7. And we're saying we circle the regions of overlap, which are going to be 3 and 6. And then we scribble out 4, we scribble out 7. And we're saying all S are in 3 and 6, which means none of them are in 2, and none of them are in 5. And so is this argument valid or invalid? And this argument, it is invalid. This one wasn't even close. Not that there is a close or near miss, but I mean this one's just terrible. It didn't even get one region shaded in the combined premises. So this argument just doesn't work. It is an invalid argument. And I hope you got that answer. So if you did, give yourself a good, firm, hearty handshake. Give yourself a good pat on the back. Attaboy. Way to go. All right, well, that's how we determine whether or not an argument with the universal conclusion is valid or invalid. Things are going to be a little trickier, and I always have somewhat of a difficult time explaining what we do with particular conclusions, but it's a little bit different. And so it starts off the same, though. So let me give you an argument that has a particular conclusion in it, and we'll work from there. So let's begin with this one. No M is P. Some M are S. 3. Some S are not P. Now, what is the mood of this argument? It would be E-I-O, and the figure is 3, E-I-O 3. So we're going to start the same way as before, and we're going to diagram the combined premises, S, P, and M. And I'm going to show you a lesson here, but I'm going to show it to you kind of in reverse. So let's say we start it and we diagram premise 2 here. We're going to kind of get out of order. We're going to diagram the minor premise first. Some M are S. M is 1, 2, 3, and 4. And the reason I'm doing it out of order is to demonstrate a point here, and I'm running out of room, but S is going to be 2, 3, 5, and 6. All right, so what we do is we circle the regions of overlap, which in this case is 2 and 3, 2 and 3. We scribble out 5 and 6 because we don't need them. And we're saying some. Now we're saying some, that means we're going to be using an X. So some are in 2 or they're in 3. I didn't do this. 3, 4, 5, 6, 7. So what do we do here? We have 2 regions. Where do we put the X? Do we put the X here? Do we put the X here? Well, what we do actually when we have an X that overlaps a region is we put the X right on the line of intersection. That might be a little bit off there. It's kind of hard with this tablet to get everything just right, but we put it there. And what that tells us is that the proposition some M are S is true if an X is in 2 or the X is in 3. By putting it on where they cross, that tells us it can be true in either case. So that's what we do when we have any instance where the X belongs in 2 regions. We don't use 2 X's, we just use 1. Now, that's actually not even the lesson I wanted to teach you. This is coming up. No M is P. Now, how do we diagram this? Well, 1, 2, 3, and 4, and P is 3, 4, 6, and 7. And we circle the regions of overlap, which are 3 and 4, 3 and 4. We scribble out 6 and 7, we don't. And this is saying no to 3 and 4. So we scribble out 4, but wait. What have we put shade there. What about 3? Because we have an X there on the line. What do? Well, what we do is we shade in 3 and we move the X over here to 2. And what this tells us, what 1 and 2 combined tells us, is that an X can only exist in 2. You can't put an X in this region because the shade rules that out. The shade rules that out. It says that basically nothing is in that region, that is completely empty. Now this goes back to what I had on the PowerPoint earlier, which is that when you have combined premises and one of them is universal, as with the first premise, the major premise, and one of them is particular, as with the minor premise, always begin with the one that has the universal quantifier, because that one tells you more definitive information. Had we started with this one, we wouldn't have had to come down here and erase and then move the X over here. I mean, logically nothing has changed by doing that. Everything logically is the same, but just from a practical standpoint, it makes more sense to just shade in all the regions first, so then you don't have to erase stuff and then move X's around. Okay? So that's what the one slide earlier I had. It didn't make a lot of sense. Led you or told you is basically when you have premises, combined premises, and one is universal and one is particular, just for practical reasons, always start with the universal one. Now, when it comes to determining whether or not this argument is valid, we also are going to draw a Venn diagram for the conclusion, just as before. And we do this just as we've done all the other ones. M, S, P, 1, 2, 3, 4, 5, 6, 7. And we're going to come down here. Sum S are not P. And S is equal to region 2, 3, 5, and 6. And P is equal to 3, 4, 6, and 7. And what do? We circle the regions of overlap, which are 3 and 6, 3 and 6. We cross those out because we don't need them. And then we're saying are not. Are not in 3. It's not in 3. It's not in 6. So where will we put our X? In 2 and 5. But look, we don't use two X's. We don't put an X on 2 and an X on 5. We put an X right here. All right? We put an X right here. And here's what you have to understand. What this proposition is saying is that some S are not P. And this proposition is true just in case the combined premises definitively put an X in either region 2 or in region 5. If the combined premises definitively put an X in one of these two regions, then the argument is in fact valid. And for that reason, this argument is valid. This argument is valid because it definitively puts an X in 2. Now, if this argument over here, if the combined premises, let's say, had put an X on this line, then we wouldn't know for certain that there's an X in region 2, because by putting it on the line, that means it floats between 1 and 2. Just as down here, it floats between 2 and 5. But it doesn't really, I was going to say it doesn't matter, but the point here is this sentence or this proposition is true just in case there's an X definitively placed in either 2 or 5 in the combined premises. So I know that's a little confusing, but what you want to do is basically, you look right here, once you diagram, let me erase that so we're not getting things in the way. Made it worse. What you do is once you diagram the conclusion, you're looking to see, okay, well, did the combined premises, did they definitively place an X in one of the two regions that the premise diagram does? That the conclusion diagram does. As long as there's a definitive X over here in one of those two regions, the argument's valid. If, the combined premises, let's say, had placed an X in region 5, the argument would be valid because it's putting the X in one of these two regions. There's actually another way to look at this, and this might even be simpler. I'm showing you the kind of, proper, full way to do it. But even the simpler way, you can actually just look at the argument and tell whether or not it's valid or invalid without even looking over here. You don't even need to look at this to tell. Now I'm going to ask you guys that, in your test and in your homework, that you do diagram the conclusion always. But just look right here and look what this is saying in S, P, and M. This conclusion says some S are not P. And here's the question. Does this X show that some S are not P? I mean, you can just look at it and say, yeah, it does show that some S are not P because it's showing that S exists in this region. But look, P, you look up here, is not region 2. Nowhere is P region 2. So it's showing that some S exists in a region that's not 3, that's not 4, that's not 6, that's not 7. So, like I said, I mean, you can just actually just look at this and tell. I'm going to ask that you always diagram the conclusion just because I want to see, all the T's crossed and all the I's dotted. But the truth of it is you can just look at it and you can know that this is a valid argument. All right, I'll give you another example, and then I'm going to give you one to practice. So let's look at another example here. Let's say premise 1. No M is P. No. All right. No M is P. Premise 2. Some S are not M. Some S are not M. And the conclusion, some S are P. Some S are P. Now what we do is we're going to do a diagram of the combined premises first. So let's begin. We're going to begin with premise 1, the major premise, because it has the universal quantifier. So no M is P. Now I'm going to, actually I was going to be lazy, but I'm not going to be lazy. 1, 2, 3, 4. And P is 3. I'm going to have to move this, sorry. M is 1, 2, 3, 4, and P is region 3, 4, 6, and 7. And we look for the regions of overlap, which are 3 and 4. 3 and 4, scribble that out. And we're saying no to 3 and 4. So we shade in 3 and 4. Now we come down here and we do the minor premise. We're going to say some S are not M. Okay. Oh, I didn't even ask you. What's the mood of this? The mood is going to be E, O, I, and the figure is figure 1. All right. So some S is 2, 3, 5, and 6, and M 1, 2, 3, 4. And we circle the regions of overlap, which would be 2 and 3. And then we're saying R not. So it's R not in 2 or 3, so it is R in 5 and 6. So what do we have done here? We have 2 regions that we can place it in. We place the X on the line. Okay, now we come to and we do the conclusion. Like I said, to do the conclusion, we just do like we've done before a million times. Actually, sorry, my diagram here is, I need more room to work with. This thing is really giving me a headache, as you can tell. There we go. Making it rain, people. All right. Progress. S, P, M, 1, 2, 3, 4, 5, 6, 7. And we have some, this is our conclusion, some S, R, P. Now how do we show this? S is 2, 3, 5, and 6. And P is 3, 4, 6, and 7. Circle the regions of overlap, which are 3 and 6. And scribble that out. We're saying R. So it is in 3 and 6. So how do we show it's in these two regions, 3 and 6? We place it on the line. Now, question here. The combined premises, in order to prove that this statement is true, it has to definitively put an X in either region 3 or definitively in 6. Does it do that? Well, no, it doesn't put an X in 3 because it shaded that out. Now it has an X right here on the border between 5 or 6, but is that definitively in 6? No, because that X floats between 5 and 6. It's not definitively here. In order for it to be definitively in region 6, it'd have to be right there, which it isn't. I know it seems like a minor thing because it's just right there, but that means we can't know for certain that it belongs in 6. And for that reason, this argument is invalid. All right, well, I'm going to give you one I want you to practice on your own. You're going to have to pause the video lecture and do it by yourself, just because I want to make sure that you guys are getting this and have some sense before I unleash you on your homework assignment. So let me see if I can get this cleared and then we can move along. So here's the one I want you to do. Some P are not M. 2. No S is M. And then finally 3. Some S are P. Okay? So I want you to do that one really quickly and see if you can determine whether or not it's valid or invalid. All right, well, let's look and see what you came up with. So what you do is you begin by diagramming the combined premises. And hopefully you realize that you need to start by diagramming the minor premise because that has the universal quantifier. Also, I didn't ask this, but what is the mood of this? Do you know? It would be O, E, I. And what is the figure? Figure 2. But let's begin by diagramming no S is M. How do we do this? Well, 2, 3, 5, and 6. Just as before. M, 1, 2, 3, 4. We look for the regions of overlap, which the regions of overlap are going to be 2 and 3, and 2 and 3. And then we scribble that out. And then we're saying no to 2 and 3. So we shade in 3 and we shade in 2. Right? So that's how we show that. Now we come to diagramming the major premise. And again, the reason we started with the minor premise is because it had the universal quantifier. So we're going to move on. Some P are not M. Notice the are not. P is 3, 4, 6, and 7. And M is 1, 2, 3, and 4. So we look for the regions of overlap, 3 and 4, and 3 and 4. Scribble that out. And we're saying are not. Are not in 3 and 4. So that means they are in 6 and 7, which means we come down here and we place an X right on that line because we know that it can go in either one of those two regions. Now, we come and we diagram our conclusion. And our conclusion is going to be just like all the other diagrams. S, M, and P. 1, 2, 3, 4, 5, 6, 7. All right, and the conclusion is some S are P. Now, I mean, you can kind of look at it and tell where the writing on the wall is, but anyways, we're going to just pretend like we can't. 2, S is 2, 3, 5, and 6, and P is 3, 4, 6, and 7. Where do they overlap? 3, 3, 6, 6. Scribble that out, scribble that out. R in saying some are in 3 and 6, so we put an X right here. And so the this argument is valid just in case the combined premises definitively put an x in region 3 or 6. Now, does it definitively put an x in either of these? Well, it doesn't put one in 3 because it scribbled that out. We shaded that in. How about down here? Does it definitively put an x in 6? No, because this x right here is on the line between 6 and 7. It floats between the two. So this argument is not valid. This argument is invalid. Yay for invalidity. All right. This argument is invalid. In order to be valid, what it would have to have done is if, for instance, it had put an x right here, it would be valid in that case. Now, as I was saying earlier, the writing was kind of on the wall. I mean, you could have just looked at this and told that, all right, look at this, some s or p. Does this right here definitively show that some s or p? No, because this is saying the x could exist over here in region 7. But region 7, if you notice up here, that's not a part of S, right? So they would be saying that some x, or if it was right here, it would be saying that some p are not S, right? It would be saying some things exist in this region which are not a part of S, which is just, you know, contradicting that statement right there. So anyway, I should say contradiction, but some, well, what would that be? Some P are not S. I don't know. I can't think quickly enough, but those two statements are not consistent. So that's the big thing. So in any event, this argument was invalid. Now, I want to give you guys your homework assignment. And if I can get my slides to change here, we'll skip through this. These are some arguments we went through. Whoa. Went a little too quickly there. But here's your homework assignment. Also, I'm going to ask that you read, and I'll put this on Blackboard for you to see, but I'm going to ask that you also read through pages 198 to 202. And then you're going to do exercises on page 203. You know, I know this seems a little overwhelming at first, but the reality is like I said, you're just doing diagrams again, and it's just more of what we've already been doing, just at a slightly, you know, we're just adding one extra element to it. But if you have any questions, please shoot me an email and let me know.